All right, today 6.1, we're going to be talking about greatest common factors and factoring grouping, factor by grouping, sorry. Right. So, identifying the greatest common factor. We have already learned how to multiply two or more polynomials. Obviously, we haven't in this class yet, but we will get plenty of practice, don't worry. We now devote our study to a related operation called factoring. To factor an integer means to write the integer as a product of two or more integers. Okay, so let's focus on what that says. Okay, to factor an integer means to write an integer as a product of two or more integers. So I want you to look at, turn your attention to this. So in the product 2 times 5 is equal to 10. We have 2 and 5, they are factors of 10. So we can rewrite 10 as a product, as a factor of 2 and 5, the product of 2 and 5. Right? After the highlighted part, it says to factor a polynomial means to express a polynomial as a product of two or more polynomials. So we come down here and we can see we have this polynomial, and when it's factored, it looks like this. Okay, so all we're basically doing is we're breaking down mathematical expressions. I'm not going to go so far as to say into primes, because we can break down composites. I can't think of numbers. Composite numbers into numbers that aren't necessarily primes. But when we're talking about factoring, we are breaking down these polynomials into something smaller. Okay, they are a product, meaning that we're multiplying them. So keep that in mind whenever we get to the whole canceling part, because everybody likes to just cancel things, whatever they see. But you can only cancel factors. Okay, we begin our study of factoring by factoring integers. The number 20, for example, can be factored as 1 times 20, or 2 times 10, or 4 times 5, or 2 times 2 times 5. The product, 2 times 2 times 5, consists only of prime numbers and is called the prime factorization. Okay, so like I said, we can break numbers down into, and we'll just go ahead and look at 20 like this. So, real quick, whenever I write on sort of like the textbook, the numbers do look a little, a little jank like that. But whenever I switch over to the actual blackboard, it's nice and smooth. So, we have 20 can be broken down into 2 times 10. Right? This is obviously we're not done. This is not the prime factorization. Did we factor? Yes. But is it the prime factorization? No. Mainly because 10 can be factored even further to 2 times 5. And then we would be done. This would be our prime factorization. The greatest common factor of two or more of these integers is the largest factor common to each integer. To find the greatest common factor of two or more integers, it is often helpful to express the number as a product of prime factors. All right. So let us look at an example together. By the way, I have one really chatty cat, and you'll probably hear him quite a bit throughout the semester. I just say that because he's running around wild right now. Okay. So I want to find, and we'll do A first, and I'll let you do B. I want to find the greatest common factor of 24 and 36. Okay, so the first thing I'm going to do, let's do 24. What I'm going to do is, you guys remember making the prime factorization tree. So I'm going to write it 24, and then I'm going to go 2 times 12. Okay, well, I know 2 is prime, so I'm just going to go ahead and circle that, or square it. All right, and then I'm going to continue on. 12 can be a factor down into what? 2 times 6. And again, 2 is a prime. And then that 6 can be factored into 2 and a 3. And both of those are prime, okay? So I have completed my prime factorization of 24. Now I want to do 36. Well, I always start with 2. If it's an even number, I start with 2. So I got 2 times 18. Once again, 2 is a prime number. 18 gets broken down into 2 times 9. And again, 2 is a prime number. And then 9 can be broken down into 3 times 3, which are both prime numbers. Okay. Now, I'm going to write these like this. So I'm going to write 24, okay, is equal to, my prime factorizations are 2 times 2 times 2 times 3. My prime factorizations of 36 are 2 times 2 times 3 times 3. Okay, so we're going to ask ourselves, all right, so what do these numbers have in common? These prime factorizations have in common. Well, we've got these 2's that are common, these 2's that are common. There is no other 2's that are common, but we do have these 3's that are common. Okay, then we're going to ask ourselves, what is 2 times 2 times 3? Okay, well that's 4. 4 times 3 is 12. So 12 is our greatest common factor. I will admit this is a very long way to go about doing it. I'm certain many of you could have just looked at 24 and 36 and said, oh, the greatest number that goes into them is 12. Okay, with that said, let's do B. I'll give you a second to do B. Again, if you have any questions, go ahead and type to me. I guess nobody has yet, or rather type to the class. And if you have a private question, just message sample students. All right, so we're not even going to make a tree for B. Okay, because I mean we can look at these numbers. Let's not put an equal sign there. We'll put an arrow. The greatest common factor of 105, 40, and 60 would just be 5. Now you can make a tree, but you can just look at that and tell. All right, let's go to the next one. I believe we got another one. I guess we could show the factoring. Real quick, the reason why I do this from the textbook. In the past, I have just had I wouldn't say PowerPoint slides. I did have a Blackboard similar to this, but I'd already have examples up, and then I would speak, and then I would work the examples. But recently, it hit me. I was thinking about I wouldn't say my favorite, but probably the most impactful professor I ever had, and I was in college, and she was very impactful because she was horrible. She was my chemistry teacher, and she was very, very bad. And she was so bad that I started looking at my textbook. Now, like many of you, I'm sure, I'd never really looked at my textbook, right? I just assumed that my teachers, going through grade school, and my professors would just go ahead and teach me everything. I don't need to open my textbook, right? What's their job? Well, it turns out there is a lot of stuff in the textbook that you can learn, and that's why I teach from the textbook directly like this now. It also helps whenever if you recall, when we were up here, I was able to focus in on what the sentences are saying, and I can more clarify without the math language what things are saying. So I do teach from the textbook, and I encourage you to open it and look at it quite often throughout this semester. Also, somebody please mute your mic. Make sure your mic's muted. All right, next up, identifying the greatest common factor. So I'll do A, the hard one. You guys get to do B, the easy one. No, I'm just kidding. That's not how it works. Is it? B is always harder than A. So I'm gonna do A. All right. So I want to find the greatest common factor among each group of terms. So I need to do this in 2 steps. I need to do it first in my constants being the actual integers here. In this case, it was 7, 14, and 21. Right. So between 7, 14, and 21, I have to ask myself, what is my greatest common factor? What goes into 7, 14, and 21? Well, 7 does. That's easy. By the way, another quick note. This is how I write my 7s, and my 1s look like this. Sometimes I do go a little crazy, and my 1 might look like this. I put a nice big old flag on there, but there is a difference between my 7s and my 1s. Again, somebody please mute your mic. Make sure your mic's muted. All right, anyways, so I found the greatest common factor of my integer. Now I need to find the greatest common factor of my variable. Okay, so I've got an x cubed, x squared, and x to the 4th. So I gotta ask myself, okay, so what is the largest value of x that I can put into a 3, a 2, and a 4? Well, it would be a 2. Okay, and let me write that out similar to how we did the prime factorization tree. Just give you an idea. Okay, so let's go back to the prime factorization tree. Notice how in the prime factorization tree here, I factored out 24, 2 times 2 times 2 times 3. I factored out 36, 2 times 2 times 3 times 3. And then I just basically matched them up, right? All the 2's paired, and then that one 3 paired. And I did have some left over, but they didn't pair, and that's fine. They're left alone. They're not part of the greatest common factor part. Same thing here. I'm going to match up, pair my x's. X times x. All right, and that's it. They no longer have anything else in common. So we would say that x squared is that greatest common factor between x cubed, x squared, and x to the 4th. Y'all hear my cat? He's going to go nuts. All right, anyways, let's do, and by let's I mean you, B. Give you a few seconds to do B. Okay. Somebody just join. All right, so B, we're going to do it in 2 steps again. We're going to factor my constants and then factor my variables. All right, so my constant would be 15 and 25. What is the largest number that can go into 15 and 25? Well, that's 5. And what is the largest number that can go into a to the 4th and a cubed? Well, that would be a cubed. And what is the largest number that can go into b and b squared? Well, that would just be b. Okay, so find the greatest common factor of the terms 8c squared d to the 7th e and 6c cubed d to the 4th. Well, that's a mouthful. So we're going to start off with the constants again. So what is the largest number that can go into both 8 and 6? Okay, well that would be 2. What is the largest c value? So what is the largest multiple of c that will go into c squared and c cubed? Well, that would be c squared. And what is the, oh, we have 2 more variables, sorry. So what is the largest value of, or power of d that will go into d to the 7th and d to the 4th? Well, that would be d to the 4th. And they do not share the e, so that's it. And this is a lot of space for nothing, so let's just fill it in a little bit. I do want to remind you guys, if you have any questions, go ahead and just type it into the chat. I mean, I suppose you can speak if you want to. Just don't say your name. But again, this will be recorded and put on YouTube for another class as well. So I don't know how shy you are. Okay. Identifying the greatest common binomial factor. All right, so the binomial, let's yeah, here's what I'm gonna do. I'm gonna rewrite this just a tad. I'm gonna write this as, well, I'm gonna rewrite it normally here. A plus b, and then we're gonna say, we're not even gonna put the and, we're gonna put 2y and then a plus b. Okay. Now, looking at factors, some of you may be well versed in this. That's fine. Others of you might just be getting reintroduced to this after many years of not doing factors. So I want you to imagine if this problem was, let's connect that y. I don't like that. Let's do that. Imagine if this problem were 3x, and let's use m, and 2y and m. Okay. Notice my m would be the a plus b. Okay, that's all I did was replace a plus b by m. And that makes it a lot easier to see that in the blue, m would be what they have in common, right? 2 and 3 have nothing in common, the x and y have nothing in common, but they do have the m in common. Well, the same thing with the binomial. Okay, this would be a binomial factor of a plus b. We have a plus b in common. So we're gonna be getting used to that here in a moment, and you'll get plenty of practice, obviously. But I just want to throw out there that you can kind of think of this as just a variable all by itself, but it's obviously not. But the greatest common factor would indeed be a plus b. Okay. Okay. So factoring out the greatest common factor, the process of factoring a polynomial is the reverse process of multiplying polynomials. So that's important. The process of factoring a polynomial is the reverse process of multiplying. And here's why. Let's look at let's just finish the sentence. Both operations use the distributive property. The distributive property would be similar to AB plus AC is equal to A times B plus C. So let's write that out the best we can anyways. Actually, let's go in reverse though. I'm worried green isn't going to show up too well, so let's do this. This is actually pretty terrible. I'm sorry. I don't know why it does that. But anyways, A times B plus C, and then if we distribute, that would become AB plus AC. So distributing is the opposite operation of factoring. And of course, you can tell that if we factored an A out, we would get this. right? And of course, the example down here really drives the point home. We multiplied that 5y right here through my polynomial, and we distribute it through, and we'd get 5y cubed plus 15y squared plus 5y. And then the opposite operation, if we factored it, we would be taking a 5 out of my polynomial, and we're just getting the opposite, not opposite, the same as what we started here. So factoring and distributing, they are opposites of one another. So real quick, let's put this in our notes. By the way, these notes will be online. So we'll add this right here. These notes will be online as well as this lecture. And I'll post them after the, I don't know, I have a class right after. I would say the latest would be at noon. I'll post the notes in the video. The latest would be noon. What do you want from me? I should have got the bigger eraser for that one. All right, so factoring out the greatest common factor. It's same exercise type that we were doing earlier, except now we're going to be factoring out of a binomial or trinomial later on. And then when I say binomial and trinomial, bi means 2, right? And tri means 3. So these are binomials. They are 2 terms in a polynomial. And we'll see trinomials later. But anyway, so factor out the greatest common factor. We're going to do a first. So between 4 and 20, what would be the largest number I can factor out? Well, that would be a 4. All right. The x is only attached to the 4, so we're not going to be factoring an x out. So we're just going to simply have 4x minus 5. B. Okay. So I've got looking at my constants, 6 and 3. What's the biggest number I can pull out there? That would be a 3. And then I have a w squared and a w. Well, what is the largest I can have there? All right, this more pops up. Nobody. Oh, sorry. Didn't realize chat was going. All right, these are all. We can see you can see my cat. All right, again, these are all private messages, but they're not so much private. So if you can, just make it public. But the YouTube channel's name doesn't have a name right now. I mean, I guess I did Vol State Sherman Brown maybe, but you're gonna have a link to the first video, and in that first video, and I'll remind you also in the announcement, bookmark the page, subscribe to the account. I don't care, whatever makes it easier for you to get to it, just in case you do miss the class. Next, can we see the cat? I mean, I guess you can. Not right now though. Is he really loud to you guys? Because he's just motoring right now, man. I mean, not now, but he was. Where will I be posting the notes? I'll be posting the notes as well as the YouTube link on the announcements. Anyways, back to the example. Sorry about that. I didn't realize you guys were messaging me. I have to look back and forth. Normally, or at least what has happened, is I get a little notification on my tablet screen, and it flashes if you send it to the class. Private messages, obviously they're on another screen. I don't see them ASAP. So yeah, if you do have a question, please just unless it's very private, just go ahead and message it to the class. Anyways, okay, so 3, I can factor a 3 out of a 6 and a 3. And then I've got w squared and a w. What is the largest factor of w I can pull out? Well, that would just be w. And what remains? Well, that would be 2w. right? And if I pull out a 3w from 3w, what do I have? I have 1. Okay. So if I were to reverse this process, again, I said the process of distributing and factoring are opposites to one another. If I were to reverse this process, and in both of them, okay, I would have 4x minus 20, and that's what we started with here. And if I distributed here, I'd have 6w squared, and then I'd have plus 3w. Okay. And of course that's a mess, so I'm going to go ahead and undo those. Let's move on to the next one. Let's see, anything good? All right, now we get to some fun ones. You know, it only gets harder. That's really it. What, buddy? I'm working. Sir? All right. If you're not speaking to me, please mute your mic. Okay. Factor out the greatest common factor. Start with A. 15y cubed plus 12y to the fourth. All right, so same as before, looking at 15 and 12. What's the largest number that will go into both of them? Well, that would be 3. And what is the largest value of y that I can pull from y cubed and y to the fourth? Well, that would be y cubed. And what remains? So if I pull out a 3y cubed from 15y cubed, that would give me 5. And if I pull out a 3y cubed from 12y to the fourth, that would give me, is that a plus sign? Yeah, that'd give me plus 4y. Okay. Another way to, no, actually, never mind. Don't want to get too confusing. All right, so that's A. B. All right, so see that helps out a lot more when the chat pops up. Right. Thought some chat popped up. Maybe someone just joined. B, looking at 9, 18, and 27, what is the largest number that will go into 9, 18, and 27? Well, that's, would be 9. In this particular example, we have two variables, a and b. So we have an a to the fourth, an a to the fifth, and a to the sixth. What's the largest exponent that will go into 4, 5, and 6? Well, that would just be a 4. And then b, and b, well, that's easy. It's just b. They're all to the first power. All right, well, if I took a 9a to the fourth b out of the first term, that would just be a 1. Take it out of the second term, we'll have a minus 2a. And then out of the third, we'd have a plus 3. We'll take a squared, and then the b is no longer there. And that's it, factoring out the greatest common factor. 6. All right, so reading here, the greatest common factor of the polynomial 2x plus 5y is 1. If we factor out a greatest common factor, we have 1 times 2x plus 5y. A polynomial whose only factors are itself and 1 are called prime polynomials. So similar to prime numbers, we have prime polynomials. Prime polynomials cannot be factored, similar to how prime numbers cannot be factored. Well, the only factors would be itself and 1, rather. So we're going to look at this next example. Actually, you know what? That's actually kind of pertinent. So let's put this here as some notes. Factoring out a negative factor. Usually it's advantageous to factor out the opposite of the greatest common factor when the leading coefficient of the polynomial is negative. So it doesn't go into detail why it is advantageous, but it's advantageous because, like many of you, I don't really like dealing with negative numbers. And whenever we get into factoring, it's a lot easier to begin the factoring process whenever we have a positive number in front of the x squared. And we'll see more of that throughout the semester. But anyways, example 7 reads, factor out -3 from the polynomial. So if I factor out, let's rewrite it. Okay. So if I were to factor out a -3 from this, did y'all hear that hissing? My cats. I've got two of them. One of them's really quiet, and I guess that's the one getting chased. But anyways, if I factor out a -3, so I'm going to factor out a -3 from this first term, and if I factor out a -3 from the first term, what does it become? Okay, well, I'm essentially dividing by -3, right? And if I take a negative divided by a negative, it turns into a positive. So we've got x squared. All right, and then we're going to take a -3 out of the positive 6x. Right. Well, a 6 divided by -3, well, that just becomes -2. And then we don't deal with anything with the x yet. And then the 33. So we're going to divide -33 by -3. -33 divided by -3, it's a negative divided by negative. So it becomes a positive, and that would be 11. And that's that. More negatives. Oh, okay, so it is popping up in chat. Okay, so what is your question? Oh, I bet what happened is somebody messaged me privately, and that's why it's again, if you have a private message, do not send it to Sherman Brown. Send it to sample student. But if you have a class message or just a normal mathematical question, send it to the classroom. Or if you want to, you're more welcome to speak. So, yeah. Yes. -x squared. Yeah. Okay, so that's the whole point of this particular example, is that, yeah, you can, if you want to. If you wanted to, you can factor out just a plain old, and we'll put it down here, just a plain old 3, and I would have a -x squared plus 2x minus 11. All right, both the blue and the green are factored forms. But we're going to be focusing more on the blue. We're going to factor out the negative number because the whole point of this process is whenever we do get down into factoring quadratic equations, this is a quadratic equation, a second degree polynomial. Whenever we get into factoring quadratic equations, it is so much easier if we have that first term being positive. Right? If we have it negative, then it just throws in so many other, I won't say problems, so many different ways to factor a polynomial. Okay, because if you think about it, and we'll just go ahead and have a thought experiment here. We'll do 8. Okay, so what are my factors of 8? Well, my factors of 8 are 2 and 4, and of course, okay, we're not doing prime factorization. We're just going to do factoring here. If I were to look for two numbers that equal 8, well, my options are 2 and 4. Okay. However, if I'm looking for two numbers that'll equal 8, or I'm sorry, -8, well, then it turns into, well, it could be a -2 and a +4, or it could be a +2 and a -4. All right, so that immediately doubles our options as opposed to just plain old 2 times 4. So that's why we want a positive number in front of the x squared.